Welcome to episode 13. We're going to be talking about embedding models, which are really fundamental building blocks of most generative AI systems. So we've already talked about encoding words as numbers in a previous episode. So let's go a little bit deeper. So we've talked about bank of the river. So if we wanted to encode the word bank as a number, this is actually pretty tricky. A naive approach to this would be to encode text as numbers, where we encode each word in our dictionary as a number in a vector. So for example, if our dictionary only had 3 words in it, cats, like, and I like cats would be represented as 111, and I like would be represented as 011, because we don't have cats in I like cats. This is a problem, though, because there are 470,000 entries in a standard English dictionary, so having a dimension for each of these would be very inefficient when trying to train large AI models. And we also wouldn't get around this little issue where bank of the river, bank means one thing, and in deposited money at the bank, it means something entirely different. So ideally, we want the numbers representing bank in each of these to be different sets of numbers. So we want to actually encode something about the meaning of the text itself rather than just the word. We want to encode meaning. And what we want to do is map a word into multidimensional space of textual meaning, where each dimension corresponds to some aspect of meaning. Now, don't let me lose you here. We're going to go into detail on this whole multidimensional thing. So I think we're all familiar with the standard 2 dimensions, like the image you can see here, where we have sales of ice cream and we have temperature. And so we have 2 dimensions here. One dimension, 18, is temperature. Our other dimension, 421 in this example, is sales. So 2 different dimensions representing each data point. On the right-hand side of my screen, you can see we have a 3D plot of temperature, pressure, and humidity. This is really difficult to interpret because human brains, even though we live in a 3D world, really can only understand things in 2 dimensions or understand data in 2 dimensions. So really tricky here, but we can kind of get the idea that temperature is the first dimension here, pressure is the second dimension, and then humidity is that 3rd dimension. And if you think about it, we're multidimensional decision makers, right? If you want to decide where to go for vacation, you're not just thinking about one thing, you're thinking about many things. You're thinking about location and weather, cost and budget, walkability, is it close to places of interest, peacefulness, is it kid-friendly, is it pet-friendly, are there good running spots? We are essentially, as humans, multidimensional decision makers. We make decisions across multiple different dimensions. All right, so how do we do this practically? Well, practically, we take a ton of text from the internet. So for example, here we take the phrase, deep learning is very hard and fun. And we create a data set by just sliding across all of our text, and we have deep, which is going to be our target word. This is going to be our prediction or our label on our data. And then the blue words are context words. These are going to be input. So we're going to try to predict our target word in red based on our context words, which are in blue. So first what we need to do is we need to transform these into numbers, right? So because machines think in terms of numbers. And if you need a review on this, go back to episode 2. So we're going to transform our target word and our context words into numbers using that naive approach that I mentioned before, that where we take all of the words in a dictionary and we one-hot encode, or we just have that number for each word in that dictionary. And so our target word is going to be one element in that dictionary. Our context words will have other elements in that dictionary. So that's how we're going to encode this as numbers. We're going to do it completely naively. All right, and then we build a neural network. And our input are those context words, those blue words. And then our target, our prediction, are those target words in red. And so what we want to do is we want to be able to predict those. But what we do with the neural network architecture is we squish the sparse vector, which is the big long vector, into a smaller vector. where each dimension, we're going to try to force it to correspond to some meaning. Because when you take a very long vector and you try to squish it down, then it needs to get rid of extraneous information and only keep things that actually matter. And things that actually matter here are meaning. And so it's going to try to figure out how to squeeze that vector into something much smaller, and by doing so, actually extract the meaning of each of these words. Now, then we can take that embedding and we remove the prediction, because we actually don't care about predicting the target word. All we care is about that squished vector. So instead of having that really, really long input, now we have that squished vector. So now any input word or phrase that we put into our model will be able to get that squished vector. And that squished vector is much, much smaller. So if you think about the Standard English Dictionary, which is 470,000 words long, that would be a 470,000 long vector. Well, we can condense that down to here, 512 dimensions. So instead of 470,000, we now have 512 dimensions because each of those dimensions has to encode the meaning of the word. And this is a 2D visualization of a 512 dimensional model. These are different captions that have been embedded with a model and then placed in 2D. And what you can see here is the spatial relationship between different concepts, where people and clothes are all grouped together. Housing is all grouped together. So you can see down here, we have dining rooms and sofas and kitchens. We have places over here like the Alps and the Himalayas. We have art and animals up here. I really like this one right here, where food is its own little clump over here. And we can map this spatially because these embeddings actually embed meaning. And so things that are close in meaning are going to be more similar numbers. And now that you can embed words as numbers, you can do all sorts of things with them. You can do math on them to determine what are similar words or concepts. And we're going to talk about that when we talk about retrieval augmented generation. You can group similar concepts into clusters. You can recommend similar items. You can train machine learning models to make classifications, find patterns, and generate text. Important to note that embedding models are trained on lots and lots of data. They're trained on the corpus from usually the known internet. So vast amounts of data are used in order to train these embedding models. And if you think about these embedding models, they're essentially a compressed version of a lot of the information available on the known internet. This is really the first time in history that we have access to this much human knowledge, although it's in a compressed form. That's really cool. Okay, so you might be asking, okay, I'm still trying to figure out the dimension thing, right? How do we think about dimensions of embedding models? So I'll give you an example. And if we wanted to embed two different concepts, right? We want to embed soup and we want to embed ice cream. There might be a dimension that is focused on food versus not food. And so ice cream and soup are going to be really close together on that dimension. Another dimension might be temperature, cold and hot, and they're going to be on opposite ends of that spectrum. You might have a dimension that is flavors. And so soup will be around umami and our ice cream is going to be by sweet. You might have served in a bowl / cone or served on its own, where soup should definitely be served in a bowl or a cone, and ice cream is maybe, maybe not. And then you have a dimension that contains vegetables and shouldn't. And our bowl of soup can contain vegetables, and our ice cream definitely should not. And so these are all different dimensions of meaning. And you can see in some dimensions we're really close together, and in other dimensions we're farther apart with these two different concepts. And so what this looks like when we try to compress them into 2 dimensions, which are the visualizations I've been showing you, you can start to see interesting relationships between the data. It's not a perfect form, right? Because you have 512 dimensions that you're compressing down into only 2 dimensions, but you can start to see semantic relationships where ice cream is close to desserts, soup is close to pasta and ramen, and they're all very far away from clothes. Important to note that these models are black box models. And we've talked about that a lot in previous episodes, that these neural network based models are black box. We don't actually know what these dimensions are. So while I came up with these very fun dimensions to separate out ice cream and soup and see how similar or different they were. We don't actually know what the dimensions are in an embedding model, and most of these dimensions have to include multiple meanings. If you want to explore embedding models yourself, I highly recommend going to projector.tensorflow.org. This allows you to be able to go in this three-dimensional point map and be able to click on different concepts and see what types of concepts are close to that particular concept. So for example, here I clicked on ML. In my head, I was thinking machine learning, but of course, in most text, it's milliliters. And then the nearest points in original space are things like centimeters and millimeters and milligrams. Thank you for joining me for this episode in the AI for People Who Hate Math series. This is an unscripted series that is inspired by my conversations with people who feel like they can't conceptually understand AI because it's just too much math. And it usually is. Most AI classes, tutorials, and videos are full of math. The AI classes that I teach as a professor have math on nearly every slide. I wanted to challenge this assumption that AI could only be conceptualized by people with strong math backgrounds. Especially as AI permeates our daily lives, I think it's important that everyone understands the technology, at least conceptually. Because without it, we're putting a lot of trust into systems we don't understand. Feel free to let me know in the comments if there are topics that you want to see covered. The initial launch is 20 episodes, and I am excited to see what you think.